and diffuse scattering character in perovskite crystals and films. Roman Burkowski. Okay, so I'll tell you, at 15 minutes I'll go like this, which means it's
Thank you. Dear colleagues, thank you very much for the opportunity to see you here and for the opportunity to be here. Very nice city, very interesting. I came from Peter the Great St. Petersburg University, technical. This university is quite beautiful. It is in St. Petersburg under snow, close to the night, and here we make our science and education. I should thank Annette very much for allocating attention to the Goldschmidt tolerance factor and to the instabilities in crystals, because I will speak about the same things in some sense, but from the different perspective. Lattice instability, what it is. One can separate it into two questions. One question is which atoms should shift, and the other is what is the pattern in space of these shifts. Which atoms should shift? And here Goldschmidt tolerance factor comes into the play. Formally, it tells whether there is some free space for some particular ions. If it is less than 1, there is some free space for the A ion and for oxygen to moving towards A ion. If it is more than 1, B ion is, let's say, almost free there. We know it is not strictly the case, but formally there is free space for him. And for oxygen, there is also an opportunity to move towards B ion. I should draw your attention, it is not strictly the projection from of the unit cell, it is, let's say, artistic description, because if that would be strictly the projection, I should try plotting one atom after the other. It is more difficult to appreciate. But I will use these diagrams throughout the talk. Tolerance factor is depicted in on the bottom. And the second question is more difficult to answer. Once we know that either B or I cations do shift due to tolerance factor, we don't know whether it will be ferroelectric instability, antiferroelectric instability, or perhaps incommensurate instability. Goldschmidt tolerance factor doesn't say formally anything about it. Before trying to address this question, we should recall what the instability is and how do we understand why does it occur. This is the paper of Anderson, soft mode paper, the very famous one. And he says there is a stiffness, wave vector dependence of the stiffness. And there are short-range forces and Coulomb forces, which are competing. And the instability occurs as a result of a delicate balance between them. And after 60 years, we still think this way, as it is evident from the papers that we publish. And Anderson says, okay, we add a Lorentz correction to the short-range forces, and this renormalizes the stiffness down, and we have instability at the zone center. And this renormalization should look like this. But then we should only have ferroelectric instabilities. We shouldn't have antiferroelectric or incommensurate. But let's say the core of this study that I present is that it is not necessarily the case. If we look more carefully, when we consider all the atoms in the perovskite unit cell, the Lorentz correction becomes different. This is, let's say, I should go back again to Washington. Here are some Mason lodges, and this is triangle is from that. So we want to understand physics, and we should bring up the model that gives us the Lorentz correction. And due to this Lorentz correction, it is everything linked to the experiments, to lattice instabilities that we observe, or to diffuse scattering that we measure. On the other hand, the model has parameters, and these parameters are polarizabilities. When we compute Lorentz correction, it should be like that in the simplest case. And then these parameters we can link to tolerance factor, to electronic polarizabilities, and in the end to the values that are tabulated in the handbooks. Let's say ionic radii and polarizabilities. But because the model is very simple, and we work with a very simple one, it is possible to look inside and get the answers how it works. Why? This is the model. If we look at the dashed line, it connects the external field, which is applied to the crystal, and to the dipoles that live inside. This is similar to the model of Slater, and this is a generalization of that model to finite wave vectors, to homogeneous solutions. And what connects the field and the dipoles is the stiffness. Stiffness is linear in these two variables. But the whole situation is more complex because we have a feedback on the right. Dipoles create fields on them. So the lattice creates the fields on itself. And this is called exciting field, is due to eval this name. And this exciting field, it sums up with the external field and the total field via individual polarizabilities of the cells, of the sites in the cell, makes the resulting dipole pattern. So the idea is to solve this model, to vary polarizabilities, and to look what emerges from that. This is shortly how it is everything defined. It is very similar to lattice dynamical models, like shell model. The dipoles in the wave vector space, they are defined by 15 elements vectors enumerating the sides of the lattice plus Cartesian coordinates. And the stiffness matrix should become 15 by 15 matrix that we can analyze to find the eigenvalues, eigenvectors, and so on. The exciting field is calculated exactly as it is for shell model. So I just skip this slide. It is a summation in real space and reciprocal space. It's easy to find in the textbooks. And then, by using simple linear relations, we can find the stiffness matrix. And this stiffness matrix is composed from two contributions. One is polarizabilities. These are model parameters. And these are Coulomb coefficients that are not variables, that are defined by the geometry of perovskite. How it looks like. On the left you see the picture of Anderson. On the right it is the picture calculated by the model. And if you cross it, if you sect it, it is basically the same as on the left. But here it is landscape in 2 dimensions. And this is basically the lowest eigenvalue. So when this eigenvalue becomes 0, you apply 0 field and you obtain finite dipole pattern. So this is lattice instability. So when we want to understand the instabilities, we look when we have zeros, when with the surface touches the 0 plane. And here is a little bit of jump, but we do that. This jump is we already have 2 stiffness landscapes. And let's take them as they are, and later we understand what is the mechanics behind them. First type is with low stiffness in the high symmetry reciprocal space planes. And this is highly similar, if not to say really identical, to the first principle results of Krakauer and Yu. Here it is the frequency of the lowest energy phonon in sodium niobate. And the same picture we envisage in barium titanate. So we should, let's say, call this as a barium titanate-like picture. Another landscape is with the stiffness valleys along 110 directions. And this highly resembles what we see on the experiment in lead zirconate. If we look deeper, it is still consistent with these assignments. Green is the labeling in quotes of these cases. In barium titanate case, the eigenvector is this chain motion. Let's say people say about chain motion, chain disorder. When a BO chain moves as a whole, and the motion of these chains is independent from each other, and from this stems this wave vector independence along the valleys. And for lead zirconate case, the motion is transverse lead waves plus the waves that are similar to the antiphase rotations or tilts of oxygen octahedra. This is similar to what first principles calculations suggest. And here comes something like a revelation about which parameters give the solutions. On top, there are polarizabilities, schematic depiction of polarizabilities. The bigger is the circle, the bigger is polarizability of the corresponding lattice side. On the left, for the case of barium titanate, there is large polarizability of B-ion. And the polarizability of oxygen is similar to baguette. It is towards B-ion. And this is what one should expect from tolerance factor consideration, because these directions are the ones where the atoms are free to move. Or perhaps, if you see further, for example, there is opportunity for the electron clouds of oxygen to redistribute inside the so-called free space. This is a matter of imagination. In lead zirconate case, the polarizability of the B-ion is completely suppressed. You see this very small circle. But the polarizability of A-ion is very large, and the polarizability of oxygen is like pancake. So it easily polarizes towards lead. So it is very intuitive that these sets of polarizabilities are arising with these conditions of tolerance factor. So it seems the model just follows the intuition. Interesting thing happens when we vary the anisotropy of the oxygen polarizability. Let's say more pancake-like or more spherical. And by varying that, we vary the level of anisotropy of the stiffness landscape. And if it becomes very anisotropic, that polarizability of oxygen, we obtain incommensurate minimum at the sigma direction. And we made a systematic study of the position of the minimum as a function of axial and equatorial polarizability components of oxygen, and found that every position of the minimum is accessible in principle. But in fact, it seems that the real crystals have their polarizabilities somewhere there around the crystal, around the circle. This is, let's say, how tolerance factor is linked to the position of the stiffness minimum. It is linked via oxygen polarizability anisotropy. In the experiments, we are interested not only in the lattice instabilities, but also in the distributions of diffuse scattering. It is a direct way of probing susceptibility at finite wave vectors, or stiffness. In principle, stiffness is how hard is your soft mode. And this is the comparison of the calculations of diffuse scattering with what is measured experimentally. On the top you see shining diffuse planes of sodium niobate. It is roughly the same as calculation gives. When the polarizability of oxygen is nearly isotropic. The second row, there is no special anisotropy also in the stiffness landscape. And this is something that we see in lead titanate, as Chapman et al. Report. With lead zirconate, there is strong anisotropy. It looks like butterflies, and it is similar to what we see in relaxers. And it is consistent with the experiments of Tagantsov and co-authors. And under pressure, we did also measurements of diffuse scattering, and we have registered these maxima of diffuse scattering intensity, and they are easily reproduced by the model by not very large variation of polarizability anisotropy parameters. In addition to that, a little drop from the experimental side. Diffuse scattering can be measured not only in single crystals, but we went further and did that in thin films. These films are of the thickness of 25 nanometers. It is very, very, very thin film. And still, using synchrotrons, it is possible to measure diffuse scattering in that. And temperature dependence is different, but the shape of diffuse scattering is similar, and it is consistent with what the model predicts. Then we go to this triangle from the scheme. Let's say, why does it happen? Can we understand why antiferroelectrics become antiferroelectrics or incommensurate? In other words, where from comes the minimum on the stiffness landscape? Basically, two questions. Why it first goes down and then it goes up? First, we answer why it goes down. There is a competition between lead sublattice and oxygen sublattice. Lead sublattice wants to have positive stiffness as ferroelectrics have. But the oxygen sublattice wants to have antiferrodistortive stiffness. And they are coupled. They are coupled by electric fields that they exert at each other. And if the polarizability of oxygen subsystem, the relevant components of that polarizability are large, then it overcomes the tendency to ferroelectric instability, and the initial stiffness dispersion is negative. And then why it becomes positive? Because the fields that cross-amplify the dipole patterns in lead and in oxygen sublattices, it diminishes on going towards the zone boundary. This is not due to the model, this is due to symmetry. So by simply analyzing the Coulomb terms, it is easy to understand why the predictions of the model are like they are. And this is some simple classification of perovskites with respect to their instabilities and diffuse scattering. This is a summary. On the right, it is a tolerance factor. On the left, it is the diffuse scattering character and the character of instability. And this, how it looks like within the model. How big is the polarizability? This requires some meditation, so I skip it and come to the summary. First thing is that this is the simplest way of calculating wave vector dependent Lorentz correction, but with accounting explicitly for the peculiarities of perovskite geometry in computing the Coulomb interactions. You cannot do it more simple. The next two distinctive stiffness landscapes are identified. And these landscapes are highly intuitive in the sense that what you expect from these crystals due to their crystal chemistry is actually what makes you the correct picture of the stiffness landscape. And then the competition between restoring short-range forces and destabilizing Coulomb forces is not only responsible for making ferroelectric instability, it can make also incommensurate instability or for example, antiferroelectric instability if these incommensurate phases do lock in. So basically the explanation can be in principle as simple as that. And let's say it is intuitive that much that I tend to trust this view. It is very simple, but I think it might make sense. Thank you very much.
Okay, thank you. Okay, so while the next speaker comes up and gets set up, maybe we have time for a question or two? Yes? Rafi. It's as on as it's going to get. Oh, I thought people who would ask questions come to this mic. No, I don't want to run around it.
Okay, so why don't we see many incommensurate systems then? You know, we see a lot of ferroelectrics and antiferroelectrics and not really anything in between. Or maybe there are out there, I don't know.
Here the answer is because there is a small tolerance factor. Let's say oxygen overcomes ferroelectric instability. The tendency to antiferrodistortive instability overcomes the tendency to ferroelectric instability. This model gives this answer. And then there is a question why we have so many crystals with small tolerance factor.
But like, for example, I mean, one could vary pressure or some other parameter and maybe expect to see more incommensurate systems, but they tend to lock into ferroelectric or antiferroelectric.
That question makes sense because when we apply pressure, let's say incommensurate instability becomes enhanced. This is what we determined from the experiments. And also pressure should increase the tendency towards antiferrodistortive instability because tilts, they help to reduce the volume. So perhaps this makes sense. So this model can be sensible to describe pressure effects.
Okay. Well, let's thank Roman again.
Thank you.
Okay, and I'll